Hello and welcome to today's lunch break session on the Graph and Beyond series. Graphs or networks are a powerful abstraction that help us efficiently represent and reason about complex interconnected data. Temporal graph databases are persistent graph systems that capture the changes in their vertices and edges over time. They are useful in applications where tracking and understanding the evolution of a network over time is a key aspect of the problem domain. I am Aditya, a developer at ArangoDB, and today I will talk about an open source temporal graph data store built on ArangoDB named RecallGraph. RecallGraph has multiple facets. First, RecallGraph is a Foxx microservice which runs on the embedded V8 runtime in ArangoDB. This gives it several desirable attributes. It leverages ACID transactions to update its event log, ensuring data integrity at all times. It works over a REST API, and we can access its documentation and test its endpoints using an embedded Swagger interface. It uses Foxx's unit and integration testing frameworks for its test suite, providing comprehensive test coverage. Second, RecallGraph provides a temporal data storage and access layer on top of ArangoDB's data model. This enables document-level versioning, point-in-time lookups for an individual document or a set of documents matching a filter. It also enables point-in-time graph traversals and shortest path queries on historical states of a graph. With version data, you also get recoverable deletes for free. RecallGraph also supports distributed tracing via the Open Tracing API. So now let's take a look at a simple demo, which will help us understand, or better rather visualize, what it feels like to work with a temporal graph database. So here we are looking at a very simple mind map application. So as far as mind maps go, this is quite a simple tool. So what makes this mind map special is that we not only get to see it in its current state as it is, as it appears to you right now, but we can actually go back in time to look at the state of this mind map as it was maybe during some time while it was being created. At any point of time when the mind map had been, let's say, partially prepared, and perhaps certain nodes were there and certain nodes were yet to be created. So here we are at some point in the middle of the mind map creation, where we see that I think the left side of the tree is more or less ready, but the right side of the subtree, everything that comes out of features, those nodes have yet to be added. So we can just jump around the timeline and go back all the way to the beginning of the mind map if we want, where nothing but the root node existed, or we can jump straight to the very end of the mind map where all the nodes exist, or we can pick any time point we like and jump straight to it. So it is perhaps debatable how useful this feature is in the context of a mind map, but one can easily imagine in case of several other graph applications, which I will talk about in a while, where it might be extremely helpful for the user to be able to look at not only the current state of the graph, but also any historic state of the graph, going back all the way back to the beginning of time if required, and of course conveniently jumping to any point of time in between. So that was a really quick and short demo to explain what it feels like, or what a time traveling graph looks like. You can, if you would like to experiment with this tool on your own, just log on to hivemind.vercel.app. I will provide a link to this at the end of the session as well. And just feel free to play around with it. All right, so now let's get back to our presentation. And so I will next try to briefly explain how RecallGraph keeps track of all the changes that its data go through. So what RecallGraph internally maintains is something called an event log. And I will explain how the event log works through means of, once again, a simple and short demo. And for that, we will take help from our friend Anna. Anna likes to sport a new look every season. So here we see that in the spring of 2019, she has black hair and no glasses on. whereas in the summer, she has added a pair of red glasses. So we will now see how RecallGraph internally maintains its event log and updates it to represent the state of the real world as the real world keeps on changing. So initially, RecallGraph begins by storing an entire or rather complete copy of the entity it wants to, or the object it wants to represent. So it goes from nothing to a complete object. After this has been done, whenever this object undergoes a change in the real world, RecallGraph only keeps track of the delta or the difference between the new state and the old state and stores that in its event log. So to represent the change in Anna's look from spring to summer, RecallGraph merely adds a pair of red glasses. Let's move on to autumn. So we see that in autumn, Anna has changed her hair color. She has dyed it from black to blonde. And RecallGraph tracks that by tracking the delta of her hair color going from black to blonde. Then again in the winter, Anna changes the color of her glasses, which RecallGraph tracks by changing the, or rather recording a delta of her glasses going from red to black. Then in spring, Anna loses her glasses. So RecallGraph tracks that by, again, storing a delta of her glasses going from black to nothing. And finally, in summer, Anna changes her hair color again. This time it goes to purple. And so RecallGraph records that as going from blonde to purple. So now we can answer questions like, what did Anna look like in the winter of 2019? So the way RecallGraph can do this is, since it has all the deltas of representing changes that have happened to Anna's looks since the beginning of time, or rather since RecallGraph started recording her looks, it can replay all those events from the beginning of time to arrive at the state of Anna's looks as of winter 2019. So here we see that the event log starts here with black hair, and it plays these deltas in sequence to finally arrive at the state of, generically speaking, an object at any given point in time. But there is a slight disadvantage to doing things this way, because certain nodes, certain entities may have gone through hundreds of changes. And when we want to look at their state or their historical state somewhere near the end of their life cycle, it really does not make sense to replay hundreds of events from the beginning of time, because that's a really inefficient process. It's okay if it's just a handful of events, like in the case of this example, but when an entity has gone through several hundred changes, it's no longer efficient. So RecallGraph has a way to take care of that. What it does is it records periodic snapshots. Snapshots meaning objects that store the complete state of an entity at periodic intervals. And in this case, a snapshot is taken at an interval of every 3 events. So now, again, if we want to answer the question of what Anna looked like during the winter of 2019, instead of having to replay all the events from the beginning of time, we just need to find the nearest snapshot, nearest meaning on the timeline, to the point in time that we are interested in. In this case, it is this one, wherein she is sporting blonde hair and red glasses. So effectively, that amounts to her autumn look. But from here, you see that we just need to replay one event and we get to her look for winter 2019. What's interesting about these deltas, or the way RecallGraph stores these deltas, is that these deltas are reversible. So you can not only refer to a snapshot that lies behind on the timeline to the point in time that you're interested in, we can also replay events from snapshots that lie ahead of the point in time that we are looking at. So for example, if we ask the question, what did Anna look like in the spring of 2020? We see that in this case, when we just think about the magnitude of distance, it is actually a snapshot in the future from spring of 2020 that is closer. So what RecallGraph will do in this case is, and it identifies the nearest snapshot by means of a shortest path query. So what RecallGraph will do in this case is, it will start with a snapshot representing her looks as of summer 2020, and then it will replay the one event, and it will replay that event in reverse. That delta is reversed and it is replayed to arrive at her looks as of spring 2020. So when RecallGraph uses snapshots from the future to rebuild the state of an object, it does two things. It plays the deltas in reverse, and also each delta therein is individually reversed. So I hope that somewhat explains, because this was a rather whirlwind tour of what the event log actually can do, but actually internally it's a little more complex. But I hope this serves to explain or gives a bird's eye overview of how the event log works to keep track of historical states of any data that RecallGraph internally stores. Finally, temporal graph systems can have several applications, far more impactful than what you've just seen in the demo. This can include temporal shortest path queries for GPS navigation, time-respecting path traversals for planning trips with multiple hops, maybe analyzing the spread of global epidemics via time-aware contact tracing, and of course, several types of graph analysis that involve the study of changes to a graph or its components' properties over time. So that's all from me. If you'd like to know more about RecallGraph, ArangoDB, or graph databases in general, feel free to reach out to us through any of the links listed on this slide. Thank you very much for your time, and I hope you enjoyed this lunch break talk. Bye-bye.